Yes, since recording has started. Yeah. So welcome. This is an hybrid of first class from Nalanda complex, which is going to be in a hybrid mode. So I hope that you can see my this page that I am sharing with you. Okay. So here we are starting today a new topic, which is the low power CMOS logic. Right. So the first thing is the what are the requirements? Okay. What are the requirements of of this low power CMOS logic? So you can imagine that because today most of our devices are of portable in nature, right? That means basically they are battery driven, right? Portable devices, that means they are battery driven. So if they are battery driven, then you want that device to be in its life, means to be in a state where you can operate it. That means the battery, you always want the battery to last as long as possible, right? So to achieve that, what you can do, you can make a battery which is very good,
Sir, voice
right,
cracking.
with a high milliampere hour. Or what you can do, probably you can always try to make some arrangements so that the power dissipation in a digital IC can be reduced. Right. So today we are not going to discuss the battery part, right? How we can make a super efficient battery with a high energy density, okay, high storage capacity. We are not going to discuss that. We are focusing today on the yes.
Your voice is cracking a lot.
Sorry.
Yeah,
Could
I
you
can hear
please?
your voice is
My voice is.
cracking. It may be network issue on my end.
It's you were saying that there is some noise. Are you saying this?
No, sir, your voice was cracking a lot. But now it's fine.
Okay. What about right now?
It's okay, sir.
Okay, okay. Thank you for telling that. Yeah, maybe sometime it can happen because of this. This is a new microphone that I am using. Yeah, right. So it's a battery-driven device, right? So need to limit. Then we are focusing on how, from the digital IC point of view, what are the things that we can do to reduce the power, right? So we have to do what? Need to limit the power consumption or power dissipation in a digital IC. Right? Reduce the power consumption in ICs. That's how we can do that, right? So this is a small background. Okay, if you want some more background on this or more discussion on this, so probably then what you can do, you can follow the Kang's book. Okay, so I'm writing it here. This book for this is that Kang's book. Hmm? So please follow this Kang's book for this topic. Huh? Low power CMOS logic. So here, what are the methodologies that can be used? So different methodologies have been used. For example, from the device perspective to the process perspective. Process means fabrication perspective. So one is this from device, because ultimately power will be dissipated in the device. So if you can make an efficient device, you can reduce the power where there is a loss. You can reduce it from the device or the fabrication point of view. Then that might be one way. So one is the device or process. Okay, so process means basically how you were fabricating those devices. Okay, so again, this is a part of this VLSI technology, and maybe we can discuss some of the things here, but not much on this. But rather, what we are going to focus here on this algorithmic level or the design level. Okay, design level. Design level means how you are designing this IC. Okay, from that perspective, we are going to analyze these points. Huh? So here, if you see this switching power dissipation in an IC, so here this is basically a typical typical any CMOS gate or any CMOS logic looks like, right? So you have VDD, you have the pull-up network, pull-down network, inputs, and this is the output, right? And if I have to write what is the average power that has been delivered here, then we will write it as CL VDD square into A, right? This is the switching power dissipation. We have already discussed it, right, during this CMOS power dissipation part. We have already covered this one, right? And here, if you can recall, we have also introduced another term which is called alpha, right? This alpha is called the activity factor or the switching factor. So that means, like, it is not necessary. Suppose if you consider these inputs, okay, suppose inputs are here, this clock, right? This inputs, one of the input is clock. It does not mean that the output will change whenever this input, one of the input is changing, right? Maybe this output is changing for suppose only here, okay, only here, right? And then again after 3, it is changing, right?
Excuse me, sir.
Yes.
Sir, the paper is little blurred. We are not able to follow.
The data.
The paper is blurred, sir. Like video quality is not good.
This is not visible. You are saying this.
So it is blurred. Like.
Oh, it is blur. You are saying. Okay. Then see, I do not have here that digital pen. Okay, let me try to focus it. There is an option for focus. I don't. Yeah, you are from this class? Oh, great. That at least, what is your name? Shomo. Okay, at least Shomo is here. That's nice. Okay, I am not alone now. Very good, Shomo. But let me check it out. Where is this? Here I don't see any focus option or autofocus option. Okay, I think here you have an focus option. So is it better now? Please check it once. Is it better now or no?
Sir, actually, there is some network.
So there are so many issues, you know. Here I cannot hear your voice clearly because it is. Class কি বার আছে পরে ক্লাসে পড়ে so here there are a couple of things because whatever you are saying na, here the what is called that speakers are too far and your voice is also not that way quite crystal clear. So yeah, and I have my Wacom here, but the digital one, but I do not have all the required softwares which is should be loaded, which will allow me to write here. Okay, then the other way would be I have a PDF file for this. Let me see that if I can get that. Then I will show it from there by sharing that. So and give me a minute. Huh? Yeah, I think Wacom would be the best way to go for from here. But okay, after this class, I will install all these required software and all these things here. Just give me a minute.
Sir,
Yes.
sir, you can open the camera software and share that.
Huh?
Like the camera software is there in the device. You can share the screen.
This one. No, it is not camera software. Yeah, but that probably will not detect my digital pen. No? I need the driver for that particular digital pen, right? So that is not present here. Yeah, something is there, Windows Journal, but that driver is missing, right? So yeah, what I will then try to do today from here, I will try to go through from here, and tomorrow onwards we will use this digital one. Huh? Just okay. So I will switch my camera, switch off my camera, and share the screen from here. Huh? Okay, Windows, this one. Yeah, please state. Is my screen visible?
Yes, sir. Now it's visible.
Okay, okay, okay. So this is already like which I had a PDF file from earlier class. So then unfortunately we have to do it from here, and probably I cannot do any writing here. Okay, so I will use the cursor for this today's class. So if you can see here the switching power dissipation. The switching power dissipation is alpha times of CL VDD squared F, right? Where the alpha is the activity factor or node transition factor, right? Which you have also discussed during our CMOS power dissipation, that course, right? So now this is a quite common thing so far, right? But here couple of things probably that we have not considered earlier. For example, we have considered only the output load, which is CL, right? But we also know there are some capacitances, right, at the internal nodes. For example, here you can see this is the C internal, right? So we have only considered the effect of CL, but not the C internal. But for accurate calculation of this power dissipation, we should also take care of the C internal. Particularly, C internal, you will see play a major role for some cases. For example, okay, you can see this is the same thing here, the same circuit, and you see there. These are the like variations in A and B, right? So suppose if this A is varying like this and B is varying like this, right? Here, right, and here. If they are varying like this, then just consider what will be the output or what will be the change in output or output waveform. See this output waveform. This is what gate. By the way, this is what operation? NAND operation. Is it NAND or NOR?
NOR.
NAND or NOR? Could you please say it again?
NOR.
NOR. Okay, please tell me before we go any further. This is what, NAND or NOR?
NOR.
NOR. Are you sure? This is NOR. Okay, then let's see. For 0 B1, right? Or when you can see this A and B are changing, okay, when this A is 0, B is 1, when this A is 1, B is 0, right? Then what should be the output? Then what should be the output? If the inputs are 1, 0, 0, 1 like this, 0, right? Then this V out is 0, right? You can see this V out is 0. So basically, this capacitance is not charging or discharging, right? But think about this internal node capacitance, right? This CL. What about this? See, when this A is turning, like when this transistor is turning on, right? The top PMOS is turning on. At that time, what is happening? At that time, this transistor is turning off, right? Because of this nature of this input. So this transistor is off, this transistor is on. So that means this capacitor gets charged, right? So you can see here, this is 0, this capacitor charge, then become 1, discharge, then charge, then discharge, then charge, discharge. So you can see that for these two inputs like A and B, even though the output is like 0, output is not neither charging or not discharging, right? Output is constant. So no power dissipation, but there are power dissipations, right? If you consider the internal node, this internal node capacitance, right? So if some combinations are like this, okay, so please then in that case we have to also consider the effect of internal nodes while considering the power dissipation, right? So for that, in general, what you have to write? In general, you have to write it like this: that this P average or this average power dissipation would be the summation of this n equal to 1 to n. So basically, we are considering all the capacitances. This alpha I, this is again the switching factor for that particular capacitive node. Ci Vi into VDD, right? Now you know that this Vi for this capacitor would be VDD only, right? Because this capacitor will be charged or discharged to completely to either to complete VDD or discharge from completely from VDD to 0. So here the change in voltage across this output node capacitor will be always VDD. So it becomes alpha C VDD square into A. However, if you consider for this internal nodes, then there might be, depending on like the input combinations, this capacitor might charge to VDD or it may not. So there is it is not necessary that this internal node capacitor will be completely charged to VDD. So, right. So that to consider that we have written here this VI. Right. We have to like understand what is the value of VI for any internal node capacitors. Right. So these are about the switching power losses. Other than switching power loss, there are short circuit power dissipations. You know that, right? When like if you consider for this case, if you consider there's an inverter, PMOS here and NMOS here, right? Then when the input is changing at certain point of time, will when the input is changing from 0 to VDD, right? At certain point, try to think about the voltage transfer characteristics, right? There, both the transistors would be on, right? And there will be a direct path between VDD to ground, right? In that case, so that is called the short circuit power dissipation, right? So you know how you can reduce the short circuit power dissipation by changing the slope of the input and output waveforms, right? Because more the slope, then you are giving more the time for you are giving more time, means for more time both PMOS and NMOS would be on, right? So this is first like short circuit power dissipation. This part also we have covered like earlier. Then the other one is the defined leakage, defined leakage power dissipation. For example, there will be subthreshold conduction leakage. There will be P to N, like between the body and drain. There will be a diode. There will be leakage current for that also, right? So all these things can be taken care by the device construction, right? But here, right now, we will focus on the power, like low power, how we can reduce the power consumption in a particular IC by scaling the voltage, by scaling the supply voltage, VDD. So please do not confuse it with the voltage scaling for different CMOS integrated node, right? You know that, right? When you scale down a device, you have to also scale down the supply voltage, VDD. So this is not that. Okay, this is suppose for a particular technology node, VDD is 1.5 volt. But the question is, if we can reduce the voltage from 1.5 volt to further to 1 volt without changing the dimension, then we can probably reduce the power consumption. Because you see here, the power consumption is proportional to VDD square. So if you can make it half, then the power consumption you can reduce it by 1/4. Right. So VDD plays the most important role, as you can see, in terms of power dissipation. Right. So it will be wise to, if you can, there is a way if you can reduce the VDD without probably affecting the other device performance. However, we also know when you reduce the power supply voltage, what will be the driving capability? Driving capability reduces. So that means your switching delay that will increase significantly, right? And we have also seen this type of plots earlier, where here in this left side axis we have plotted the normalized delay, right side y axis we have plotted the normalized power dissipation, and here the supply voltage. So supply voltage starting from 0 volt, if you can go from this side to VDD, then you can see as you are increasing the supply voltage, then what is happening to the normalized delay? Normalized delay is reducing, but what is happening to the power dissipation? Power dissipation is increasing. So you have to then balance like between these two. So probably you cannot like reduce the power supply that significantly so that your device delay become that high, right? So for that, what are the other things probably we can do? Okay, so here then one thing we have understood, that to reduce the delay we have to reduce the VDD, right? Okay, now if we have to reduce the VDD, then we have seen the power like the driving capability or the ID that will also reduce, right? Because ID is basically VGS become VDD, right? VDD minus threshold voltage square. I am assuming that the device is operating in the saturation, right? So it is basically VDD minus V threshold square. So we are reducing now the VDD. Then what is happening to the ID? ID is also falling down, right? But what is the impact of reduced ID? Delay will increase, right? So for that, to compensate that, probably what we can do, while we are reducing this VDD, we can also reduce the threshold voltage, right? So that would be one of the choice. But the question is, can we really do that? The answer is no. Threshold voltage of any transistor, if you want to reduce, you cannot reduce in a proportionate way to that of this VDD, because there are other challenges that will also come. I will discuss those things. Right. So here we have seen, we can see here it is written already that the threshold voltage cannot be scaled down to some extent as to the same extent as that of the power supply voltage, that is VDD. Right. Because let us discuss the why it cannot be done. Because if you have a very low threshold voltage or threshold voltage, or if you scale down the threshold voltage to an extreme level, then what will happen to the noise margin? Please think about the noise margin of an CMOS, right? So if you reduce the threshold voltage, its lower noise margin as well as the noise margin low, noise margin high, both will reduce, right? So noise margin can actually impact the performance, right? Because then the device will be more prone to or more vulnerable to the surrounding or ambient noise. And the other one is the high threshold conduction. If you reduce the sub-threshold, if you reduce the threshold voltage, then the sub-threshold current would be very, very high. I hope that you can recall that we have already drawn on plot, right? That what will, unfortunately I cannot draw it here, this, how the sub-threshold slope would look like, and what will happen if you shift the sub-threshold, if you shift the threshold voltage towards in the more left, means you can reduce the threshold voltage. Actually the relation is exponential. You reduce the threshold voltage by some amount, your your leakage current or sub-threshold leakage current will increase that much exponentially, right? So probably these are the challenges why if you want to scale down threshold VDD by half, probably you cannot do the same thing, or same scaling factor you cannot use it for the threshold voltage, right? But suppose we can do to a certain extent. For example, here you can see this is the threshold voltage of 0.5, 0.4, 0.3 for the same device. If you can reduce, if you reduce threshold voltage, then for here in the y-axis we have plotted the normalized delay, x-axis we have plotted the supply voltage. Right? Then it is quite clear. Like you take any one of the plot. For example, threshold voltage 0.5, right? The green one. Right? So if you increase the supply voltage, then what will happen? Delay will reduce. That is fine. Okay. Now what will happen? Suppose not now. Okay. So now suppose what will happen if you can further reduce it, the threshold voltage, say 0.4. Then the plot looks something like this. If it is 0.3, then the plots look like something like this. So what I am trying to say, suppose for 0.5 threshold voltage, okay, for this much VDD, say, I hope that you can follow my cursor. For this much VDD, delay is this, right? Delay is this. And suppose this delay is okay for us, right? Then you can see, if you can reduce the threshold voltage from 0.5 to 0.3, then probably you can, achieve the similar delay, okay, for here. Right, where the supply voltage is pretty low. Are you getting my point? So what I am trying to suppose for this threshold voltage 0.5, you fix the delay, that is the required delay. Say the delay is this much, right? But here the supply voltage is this. Okay. But if we are able to reduce the threshold voltage from 0.5 to 0.3 and if the plot looks something like this, then see the same delay can be achieved here with a much lower VDD. Right, so probably we can achieve much lower VDD. Much lower VDD means we are not compromising. Much lower VDD means much lower the power dissipation, but at the same time we are not compromising on the device delay or the normalized delay. Right. So then the question is how we can achieve that. So the answer is like this. It is called one of the technique is called the variable threshold CMOS. Technique, or in short it is called VT CMOS technique. Right. So it is pretty simple actually. Okay, you try to understand this diagram. This is an inverter. Right. If you just neglect this part, the right hand side part, it is a simple inverter. Right. Okay. Okay. Let us first discuss this one. This is a simple inverter, and in inverter we know for NMOS the body is been connected with the source. Right. Even for PMOS, body is been shorted with like the source. So that means the body is being connected with VDD for PMOS, and here the body terminal is connected with the ground for NMOS. However, instead of doing that, if we take the body terminal like this and do not short, but we connect it with an additional circuitry, which is we call it as substrate bias control circuit, then this control circuit can provide bias accordingly, okay, to this as well as to this. Obviously, they are different values. For PMOS it is different, for NMOS it is different. Then basically what we are doing, we are actually giving different voltages to the base terminal, right, compared to this one. And you know the effect of the body bias. I think some of you have told like you need some more discussion on the body bias. Okay, so we are not going to discuss it today. Maybe possible tomorrow or in the next week. Definitely we will discuss more on the effect of body bias from some device physics point of view. Huh? Okay, but for today let us only understand this part, that if we apply some body bias, obviously threshold voltage is going to be affected. Right, now how can you give some body bias which makes the PN junction forward bias? No, you have to always apply. Are you getting my point? Body bias. Body bias means for PMOS it is body is of N type, right? So obviously you have to give some voltage here which is positive, right, to make that PN junction. PN junction means drain to this body, PN junction reverse bias. You cannot apply some forward bias, right? Then there will be a current flowing from the body to the drain. You don't want that. So you have to always keep the reverse bias. Okay. So initially you see here initial case, like for example for here, when this VSB source to body is 0, source to body is 0 means this is the source, right? Source is at 2 volt, body is at 2 volt. So here, okay, we are applying 2 volt. We are giving a term here, or writing a term here, which is called the active mode. So in active mode, we are giving 2 volt here. Here also in active mode, this is supplying and 0 volt here. So basically, when you are applying 2 volt and 0 volt, basically it becomes a normal inverter. However, okay. However, in standby mode means when the device is not operating, means input is not switching. The input is not changing. So if there is no input change, output should not change. So if there is no input change, then it will change by this circuitry, and it will increase the voltage to the both this base as well as this base. So in the standby mode, it increases to 4 volt, and here it increases to minus 2 volt or decrease to minus 2 volt. Right. So you can see here, you are basically making this PN junction here as well as here more reverse bias. So when you do that, your threshold voltage becomes more and more negative. Sorry, threshold voltage actually increases. Okay. So I think I will discuss it in a separate context, means separate in a class, like what is the physical effect and how why it is changing or why it is increasing. But for the time being, only understand here this, that if you make the this body bias voltage change from 2 to 4 volt, then for PMOS the threshold voltage become more negative, so 0.2 volt to 0.5 volt. If we do the same for this NMOS, suppose we are changing this voltage from 0 to minus 2 volt, then the threshold voltage will become 0.2 volt to 0.5 volt. Now you might ask why we are doing this, because we want, during the switching condition, we want the threshold voltage to be lower, because we have to reduce the delay. The reason behind is that we have reduced the VDD, right? We have reduced the VDD, so that driving capability has reduced, right? To accommodate that, we should also reduce the threshold voltage, so that the delay can be further reduced. So during transition or during switching, we are able to reduce the threshold voltage by controlling the this body bias. However, when it is not switching or it is in standby or in sleep mode, right, at that time what we are doing, we are giving some voltage, so that the threshold voltage, we are giving some voltage to the base terminal or to the body terminal, so that the threshold voltage becomes much more higher. So what will happen, threshold voltage becomes much more higher means your gate leakage will further reduce. So that is the whole point here, right? Okay, so the same thing has been written here. Anyway, I will share this with you. So in active mode, you can see the threshold, VBN is this. So this is the like body to and VBP or VDD is this. So then what is the total base, total body to drain bias, that you can calculate obviously. Okay, so this I am going to discuss in a separate class. Now, another technique would be to use this multiple threshold voltage CMOS, right? So in this technique, what you basically do, you insert two different types of MOSFETs. The inner one, okay, or which you are using for it your logic purpose, or constructing the logic purpose. For example, you can see here this is an inverter operation. Yeah, it cannot be only inverter. You can make it say NAND gate. So accordingly, you can put the NAND block here, right? But for this transistor, the threshold voltage should be extremely low. Threshold voltage is quite low. Okay. Now you can see we have two more transistors guarding this. Okay, one is above, one below. Above one is PMOS, bottom one is this NMOS. These are the transistors where we have used the high threshold voltage. So these are high threshold voltage PMOS, and these are also high threshold voltage NMOS, right? So what you will do during standby means when it is not switching, then you turn on, means then you apply this, means then you apply here say like 0 volt and apply here sorry, you apply here 1 volt and apply here say 0 volt. As the threshold voltage is higher, then what will be the leakage current? Leakage current will be lower. So the overall leakage from VDD to ground that have to reduce, right? But what is happening in the active mode? So in the active mode, this is, you have given here 0, you have given here 1. So this is conducting, right? But this one, okay, which defines the current here. So here, okay, for this one, the driving capability can be increased or is increased because of this lower threshold voltage. Right? So basically compared to the previous one where you are changing the threshold voltage by using an external circuit, we have like fixed we have two fixed, two transistors on the bottom and the top part of this logic network, which will reduce the static power dissipation in the standby mode, and the inner one, the inner logic block, which where we have used the low threshold, which will increase the driving capability and reduce the delay. So all these things are written here. So that is the like most important thing that you should know. But overall, there are obviously some disadvantages because you are using 2 transistors on top of this. So the overall circuit area, it will increase. Additional parasitic capacitance because of this standby, like these 2 PMOS and NMOS. These things will also come, right? But the important thing is here, what about the size or width of this standby transistor? So obviously you want during active condition, this PMOS and NMOS that has to offer the lowest on resistance, right? So that the voltage drop across this and this should be reduced so that you get the maximum current. So for that, what you have to do, you have to increase the size of this PMOS as well as this standby NMOS. There are other approaches as well, which is called the technology mapping. So basically in technology mapping, so okay, let us consider then from this point. So we have seen the power, like average power dissipation is alpha CL VDD square A. So it is VDD square. We have already considered what will be the effect of reducing VDD and how can you reduce this VDD, right? Okay, what is CL? CL probably we have also considered, like how can you minimize the CL, right? During delay, during I think we have lot of discussion, right? How can you reduce the CL, right? Now what about F? Frequency. Yeah, frequency obviously you can reduce it. Maybe this discussion we will take it up in the next class. But here in technology mapping, what we will address? We will address this alpha, that is the switching activity, or this activity switching. Basically, is the switching activity only. So the thing is that how do you define switching activity? Before that, we should know. Say these are the common gates. Okay, here these are all gates are like first 4 gates are 2 input gates. The last gate is the 4 input gates. Okay, so here inputs are A, B, A, B. So we have defined 2 probability factor. One is PA, other one is PB. PA is what? PA is the probability. Like PA is the probability of this input A to be equal to 1. 1 is logic 1. PB is the probability of input B to be logic 1. Okay, what is PF? PF is the probability of this output to be logic 1. Right? So you see, then this is PA, this is PB. Now you understand PA means the input to be logic 1, PB means this input to be logic 1. Right? And PF is the probability for the output to be logic 1. Right? Then this is an AND gate. Right? Then what will be the PF? PF means the probability that the output would be 1. How do you get it? When both would be 1, then only the output would be 1 for AND gate. So it will be the multiplication of these 2 probabilities. So it is PA, PB. Right? Okay. Let us consider the third one first. So this is AND gate. Third one is the NAND gate. So for NAND gate, it will be just 1 minus of this AND gate. Right? So here the PA would be 1 minus of the probability of this AND gate. That's how you will get for NAND gate. Okay. Now let us come to this OR gate. So for OR gate, it is what? Okay, OR gate, when you get 1, when at least one of the input is 1, right? So when at least one of the input is 1, How do you find it? Or what I can say, when both the inputs are 0, then the output would be equal to 0. Right. When both the inputs would be equal to 0, when it is 1 minus PA into 1 minus PB. Right. So this factor will give the probability when probability of output to be equal to 0. Now if you substitute that one from this whole number 1, then you will get the probability of output to be equal to 1 for this order. Similarly, this is for NOR gate, so it will be again 1 minus of minus this, so you will get this. Right. So if you consider for this 4 input AND gate, then here the probability factor would be, or probability of output to be equal to 1 would be this PA, PB, PEC into PD. Right. Okay. Now what do you mean by the switching activity? Switching activity is what? When the output is changing from 0 to 1. Right. So when the output is changing from, remember, when the output is changing from 0 to 1. Okay. What is the probability that the output is 0? It is 1 minus of PF. What is the probability that output would be equal to 1? It is PF. Right. So if you multiply these two, then that will give the transition probability or the switching probability. Right. Because only during switching the power will be dissipated. If you are considering, right now we are considering the switching power dissipation. I hope this part is clear to you. If it is yes, then let us see one example here. Say we have to design a 4 input AND gate. So you can see here, this is a 4 input AND gate, and here the probability factors are written like this. PA is 0.2, PB is 0.2, PC is 0.5, PD is 0.5. So what does this mean? That means the PA, like the probability of the input A to be equal to 1 is 20%. That means this, and the probability of this input D to be equal to 1 is 50%. Right. Now, we will also discuss this part bit later on. So actually, it is not good to have a very high fanning. We will discuss this part separately. Why it is not good to design a gate? Suppose, have you seen like 10 input AND gate, 10 input NAND gate? No, right? Because there are some practical limitations why we cannot do that. So that way fanning is also limited. Obviously, we have discussed the fan out, right? Fan out is limited by what that we know. But fanning, we will discuss it. So probably we have to split it. So suppose designer 1 designs it like this: A, B, C, D. Okay, output of this two connect with this, output of this connected with this. So this is one of the design. Second designer designs it like this. So the output of both are the same, right? No doubt in that. Right. Now let us consider or analyze these two design from the power dissipation perspective. Okay, or from the switching activity point of view. See, for design 1, okay, here what is PE? PE is the output to be equal to 1. What is PE? It will be PAPB. So these values are given, multiplied. So you get what is this PB, right? Then what is alpha E? Because you have to also calculate what is the switching factor of at this node E. So alpha E would be equal to PE. That is the we have already discussed it, right? PE into 1 minus of PE. So this is the alpha E. So the probability means switching probability at node E, right? Similarly, you can find the switching probability at node F, right? If you can find the switching probability of node F, then D is also probability is given. So you can find the switching probability of this node G, the final node as well, right? Then what will be the total switching activity? Because remember this is one capacitor. Node E means it is driving one capacitor, right? This one. Node F means this is also driving another capacitor. Node G is also driving another capacitor. So what is the total switching activity? Total switching activity would be the summation of this and this. So this is the total switching activity. So total switching activity, simply have to add all the switching like nodal activities, right? So it is, try to remember the value, it is 0.0679. Okay. So let us now consider the design 2, which is this. So here we have two internal nodes X and Y. So you can calculate what is Px, what is Py. We can also calculate alpha X, alpha Y. Right? Okay. And okay, after you find what is alpha X, alpha Y, you have to also find what is alpha Z. Right? Then what here in this case, what is the total switching activity? Total switching activity is, if you have to add again these three. So if you add these three, it is coming out to be 0.235. So you can see the design 1, the switching activity is much lower compared to the design 2, right? So obviously then from this point of view, from this particular case, or for this chain structure, the design 1 has lower switching activity compared to the next structure, which is actually tree type, right? This design is called it's called the chain type, okay, and you can see here it is the tree type design, right? However, if you consider from the delay point of view, maybe your requirement would be different, right? So for power perspective, you can analyze any circuit like this, okay. So we are discussing it from different context. We are first saying that can we reduce the VDD? Next question is, can you reduce CL? Then can you reduce F, the frequency or clock frequency? Then can you reduce the switching activity? All these things. Okay. So it is not like that. Okay, we will think only for switching activity, only for reducing VD, only for the frequency. Not like that. Okay. All these things should come simultaneously. Okay, while you are designing. Right. Now, suppose in the previous design itself, the values has been changed. Okay, so previously the values of this PA, PB were like 0.2, 0.2, 0.5, 0.5, right? I think if you recall here, 0.2, 0.2, 0.5, 0.5. Now suppose you have interchanged it, okay? Make 0.5, 0.5, 0.2, 0.2. Okay, like here 0.5, 0.5, 0.2, 0.2. Okay, now consider the case. Now see that which design is good. So again, I am not going through the again thing, it is the same thing, you can do it. So here for the first design, you see now the this alpha, the total switching activity it becomes 0.24, whereas for design 2, it is now becoming 0.2358. Right? Now compare the results. Now they are almost quite close. Right? So it also not necessarily like that, tree type or this chain type would be better for any design. It also depends what are the switching activity of these nodes. Okay. Then there is one more technique which is called the input ordering. So input ordering means, I think you should have noticed from these two that here what we are means why here the switching activity was so low, right? Because we have introduced the high probability nodes later on. Have you noticed this? See PC later on, PD later on, right? But here that we have introduced PC here in the stage 2 itself, right? Because see, and in the next case, here we have introduced 0.5, 0.5, right? So switching activity here will be very high. If this switches too fast, that means here also the switching will be quite fast. If this switches fast, then what will happen here? This also has to switch fast. If this switch fast, then what will happen here? This has to also switch fast, right? So one of the common technique is, if some node is switching quite fast, then try to put it more towards in the like output, closer to the output node, right? Probably we'll see it here. So it is called the input reordering. So you can see it here. It is basically what we are getting here. It is ABC, right? Z equal to ABC for either case, right? But the probability is something like this: 0.5, 0.2, and 0.1, right? So for design 1, we can say the total alpha is becoming 0.099, right? Whereas in design 2, this alpha is becoming 0.0295. So obviously, design 2 is more power efficient because it is having the lower switching activity. Right. Now, what is the reason? So it is beneficial to postpone the introduction of input signal that has a high transition rate. Okay. For example, here in this example, which is input A. Right. So here you can see it again. This input A has a transition probability of 0.5. Right. And here we have introduced it here. But here we have introduced in the design 2, we have introduced it in a much later state, right? So obviously this design 2, from this itself you can say the design 2 would be much more power efficient compared to design 1, right? Okay. So now a bit more on understanding on this. So for example, we are again continuing the switching activity part. Let us consider the CMOS NOR 2 gate. So for NOR 2 gate, this is the truth table, right? So for only for 0 0 the output is 1. For any other combination, output would be equal to 0. So what are the input combination? Input combinations are either 0 0, 0 1, 1 0 or 1 1, right? And this input combination, like any of the input, have an equal chance to occur, right? So that way we can say that this P output, like this P naught, that P naught means the probability of this output is to be equal to 0 is 3 by 4, right? You can see from here. The probability of output to be 0 is 3 by 4, probability of output to be 1 is 1 by 4. Right? Okay. Then what is the transition? What is the transition probability from this output node for this output node to make a transition from 0 to 1? That would be what you have to multiply it from this P0 P1. So if you do that, it is 3 by 16. Right. Now let us say for different transitions. Okay. For like initially it was at 0. Now it has to go to 1. Are you getting my point? This is a state diagram, right? Initially the output was 0, now it has to go to 1. Okay. Then what is the probability? The probability is 3 by 16. Right? Okay. Suppose from 0 to 0. Okay. What is the probability? It is 9 by 16. Okay. From 1 to 1, what is the probability? The probability is again 1 by 4. You can calculate it from here, right? 1 by 4. It is 1 by 16. Here the opposite one, that is from transition probability from 1 to 0 is again 3 by 16. Right. So it is basically the state transition diagram and state transition probabilities for this NOR 2 gate. So similarly, if any gate is being given to you, new gate, you should be able to find what are the transition probabilities from one state to other state, and depending on that, you should be able to find what are the total switching activity in a particular design, right? Detail IC design. Yeah, so I think let us stop here. Okay, it's already around 1, and we also have to install the software here. So we'll stop here and we'll start from here tomorrow. Okay, okay then. Thank you.